Okay, as we learned through the capabilities of neural networks and we saw that they are information processors. So, let us look into the details of these neural networks, right. One of the most basic unit of a neural network is a neuron, and we should start with models for these neurons, or they are also called processing elements, and then with this basic object we start building a collection of neurons and then we endow it with certain features and we say this is a network. Okay. So, let us get started with this. A neuron is an information processing element, and it is basically a fundamental unit. Now, what is it capable of? So, we have to describe it in a little more precise way. So, we have these external inputs we have x1, x2, so on till xm, and then we have weights connecting these inputs. So, I call them WK1. So, this is the kth neuron and the signal x1 is connected to the kth neuron. So, similarly this is WK2 dot 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 WKM, right. It is basically scaling these inputs, and then we add a bias which is BK, and at this stage I would say it is a linear combiner. This gives us a signal which is Vk, and this goes through an activation function. I will talk about this in a short while, what this activation function is, and then I have an output. I call this Yk. So, this is my simplest form of description for a neuron, and one might question here, why should I have a linear combiner here, can I not have some other non-linearity, etc. Says this is a model to start with. So, I basically collect all the stimuli, scale them with the appropriate weights, and I add a bias. This is where I can adjust the firing of this neuron, I can control this bias, and this linear signal that I have, I pass it through an activation function which is non-linear typically, and then I have an output response, right. This is sort of an abstract model for a neuron, right, and this has some biological plausibility. For example, these points here, right, you can think of them as synapses which are connecting links from the kth neuron to the signal xj at your at the input of the synapse. So, there is some motivation to that, but in biology we do not know exactly what is happening because we need models to describe them, and we want to abstract them as closely or as better as possible through these mathematical models. Okay. So, So, let us start with the basic equations. UK is basically sigma j equals 1 to m, that is you are summing over all the sensory inputs, j going from 1 to m and scaled by the corresponding weight wk comma j, right, and this is what we had here. And our signal Vk is uk plus this bias. Now your yk is basically phi of uk plus vk, which is basically phi of vk that we just described. So one can think about how this would look like. You know, if it is very it's easy for us to kind of imagine how this looks. If we can plot this, so this is UK and this is VK, right. UK is basically this linear combiner and VK is with the bias. So this is basically a straight line, right. This is straightforward to guess, and if BK is this line has to be, if BK is positive, you have a positive y intercept. If BK is 0, you have a line that is going through the origin, and if BK is negative, you have a y intercept which is negative, right. This is basically an affine map. So we have this structure for the neuron, and throughout the course we will see this this structure, except that the activation function can be different and the network can be different from the neuron, but in general the processing element can be described in this way. So you can kind of interpret this bias here as having an input which is all 1, which is essentially a 1, and then you scale it with this BK and then you feed this to the linear combiner, right. That is how you can interpret this bias term. Now let us get into the types of activation functions. The simplest would be the threshold function, and this is also the McCulloch-Pitts model. So this is described by a simple Heaviside function phi of v. So v is our local induced field and phi of v is basically 1 if v is greater than or equal to 0 and it is 0 else. And yk is essentially this output which is phi of v. So therefore yk is 1 if the local induced field is 0 or positive and it is 0 otherwise, right. A sketch of this is as follows. So I will just put this in black. So this is a very simple activation function, right, and we can think about how we form our decisions, right. So, if I have it's raining, it's very badly raining, I'm sure I will not step out of the house, it's very badly raining, and I know it is not raining, I move out of the house, I can go out, right, and so it's a 1 or a 0 decision. So, these decisions we form, right, and even in the brain there is enough evidence where we make a clear yes, clear no when we take decisions, and this is the motivation to having these Heaviside functions. So, this is the hard limiter. So, one may also have a function which is not a hard limiter, and this would be the sigmoid, for example. The sigmoid function is given by phi of v, which is equal to 1 upon 1 plus exponential a times v, and is also called the logistic function. So, if you just investigate how this function looks, I mean you can plot the sketch. Exponential of minus a v is an exponential decaying function if a is positive, and you add one bias and you take the inverse of it, and you can think about how to sketch this. I would leave this as an exercise to plot this sigmoid function. So, you can think about this as, I mean, why this is, we have this this formulation than the threshold function. The threshold function is not differentiable at the origin, it is discontinuous, whereas the sigmoid function, it is a smooth function and it is differentiable at the origin. So, if you were to derive learning rules where you will have to take derivative of the activation function, then we will have to endow it with certain properties, and that is the reason why we can choose this function. Okay. And you can guess when v is really very large for a fixed a, right, exponential of minus a v is basically 0, and you have a 1 there, it saturates at 1, and then you can think about the other case when v is strongly negative, that this is a very positive quantity here, and 1 upon a large quantity is essentially 0. Okay. One can think of other functions for activation. This is the signum function. This sine function is as follows, is 1 when v is positive, 0 when v equals 0 because 0 does not have a sign, minus 1 when v is negative. So, this is another form of activation, but this is still like a hard function, like the way we had the Heaviside function. This is a hard function except that it is plus 1 and a minus 1, is not a 1 and a 0, right. The sigmoid is a more smooth function. We also have stochastic neuronal models. So, when I describe the stochastic neuronal model, we will try to link this to the other models that we just described. The motivation to stochastic neuronal models stem from the stochastic resonance effect in neurobiology. So, what is this stochastic resonance effect? So, you can have noisy neurons and still you can have intelligent information because you can cancel this noise in some way. So, if you have faulty gates or faulty components, the inherent noise because of these faulty gates can cancel themselves and tend to provide noise immunity towards better error correction than what you can have without it. So, this is the stochastic resonance effect, And when we think about engineering neuromorphic systems, we can have stochastic neuronal models wherein the firing of the neuron is stochastic in nature, and this can lend itself to interesting nonlinear dynamics which can be potentially providing you noise immunity, right. With that motivation in mind, we will derive the stochastic neuronal model. So, let us describe this. Let the decision for a neuron to fire be probabilistic, right. Let x be the state of the neuron, and this state of the neuron is +1 with a probability p, and it is 0 with a probability 1 minus p. This is like a Bernoulli process, right. So, I am in state plus I take this value, the state of the neuron is +1 with a probability p, and it is 0 otherwise. And this probability p is some function of the local induced field and a parameter t that controls the noise level and decides the uncertainty in firing, right. And this can be typically given as 1 upon 1 plus exponential minus v upon t. And when t heads to 0, this implies this is the noiseless case, and this leads us to the McCulloch-Pitts model, right. When t goes to 0, 1 upon 0 is infinity, this is strongly negative. So, this basically goes to 0. So, therefore, p becomes 1, that is, it is deterministic with probability 1, this takes a particular state which is 1 and it is 0 otherwise, right. This is like the deterministic McCulloch-Pitts model. So, and one can think about this parameter t as like the annealing parameter, and this can control the thermal fluctuations or the synaptic noise, and you can, given this parameter t, you can adjust your firing threshold. Yeah, as I discussed earlier, the role of stochastic neuronal models is very important in engineering artificial systems that are noise immune, and this comes from the stochastic resonance effect that is seen in biological systems which are inherently immune to noise, right. And if you want to bring in and engineer systems and neuromorphic systems that are capable of exhibiting the stochastic resonance effect, then it would be useful for us to use the stochastic neuronal models. Okay, now we will start with the interpretation of neural networks as digraphs. Digraphs mean directed graphs. Okay, so let us sketch this out. So, x naught is 1, that is giving us this bias component, and then we have x 1 so on and so forth till x m. We will connect this through edges to the linear combiner, and we have an output y k. through the activation function. So, what is important here is to see that there are directed edges from the source to the destination, right, and that is why it is thought about as a digraph. And there is a signal flow that is happening through this system, and when we think about signal flow, then we have to describe in terms of signal flow graphs and rules associated with those. So, we will state these rules in a coherent way and then we will see the connections. Rule 1: a signal flows along a link only in the direction defined by the arrow on the link. So, we have synaptic links and we have activation links. So, let us describe them carefully. Synaptic links, we have a node signal xj and this is scaled by a synaptic weight wkj. I have used k comma j, so I will put a comma here. To produce yk. Sometimes I may not put a comma, but I think it is implied that wkj is basically synaptic weight that connects signal j to neuron k. And we have activation links and the behavior of these activation links is governed by the activation function, by the nonlinear input output relationship. This is rule 1. We have rule 2. A node signal equals the algebraic sum of all signals entering the node via incoming links. This is one of the rules. This is the second rule, and it makes sense, intuitive sense, because you take these stimuli, you scale them by the corresponding weights, synaptic weights, and then you linearly combine them, right, and then you force it through some activation function. We have rule 3. The signal at a node is transmitted to each outgoing link originating from that node and this transmission is entirely independent of the transfer functions of the outgoing links, and that transmission is entirely independent of the transfer functions of the outgoing links. This is very important. So, in this context you can think about signal flow graphs like the way you have seen them in control systems as pioneered by Mason, and this was successfully used in signal processing, coding and all these applications. For example, when you think about error correction coding, when you have to look at the weight enumeration function, you can use the signal flow graph idea. And similarly in control systems, if you want to simplify the transfer functions, you use signal flow graphs, and in a similar way we can think about it in the context of neural networks, except that we have some non-linearities here, and it is not like a transfer function that we think about in the traditional sense, but sort of mappings. But this idea of having representation through digraphs gives us a clear picture as to what the inputs are and how the signal is flowing and in which configuration, if there is feed forward, if there is feedback or there is no feedback, etc. Right. So, this is an important way to represent a network using directed graphs. So, with this we are ready to get into the idea of feedback and understand what the feedback mechanism is. We will stop here.